In the last several videos, we've been talking about doing a kind of abstract computation, computing with elements like bottom, the constants, and top. And in this video, we're going to start to generalize those ideas a little bit. And the first thing we're going to talk about, the first step towards that generalization, is to talk about orderings of those values. First, I'd like to introduce a technical term. These values that we compute with in program analysis, things like bottom, the constants, and top, these are called abstract values. And that's to distinguish them from the concrete values. So the concrete values are the actual runtime values that a program computes with, things like actual objects and numbers and things like that. And the abstract values here that the program analysis uses are, in general, more abstract. So in particular, abstract values can stand for a set of possible concrete values. And in the particular set of abstract values we're using for constant propagation, there's really only one very abstract value, and that's top, and it stands for any possible runtime value. So it stands for the entire set of runtime values. Anyway, it turns out that there is a way to simplify the presentation of the analysis that we've been discussing by ordering the abstract values. So what we're going to say is that bottom is less than all the constants, and all the constants are less than top. And so if we draw a picture with the lower values drawn towards the bottom of the picture and the higher values drawn at the top, and edges between values where there's a relationship, we get this diagram here. So you have bottom down here underneath all the other values. Bottom is less than every constant. Okay, so notice that all the constants are here on the middle level. All right, and also notice that the constants are not comparable to each other. All right, so this ordering is different than the numeric ordering. So 0 is not less than 1, for example. 0 and 1 are incomparable, as are every other pair of constants. So you have bottom at the bottom, you have all the constants in the middle, and they're incomparable, and then bigger than everything else is top. Now, with the ordering defined, there's a useful operation we can define on collections of elements, and that is the least upper bound, or LUB. All right? And what this means is taking the smallest element that is bigger than everything in the least upper bound. So for example, if I have the least upper bound of bottom and 1, that is equal to 1. Okay? If I have the least upper bound of top and bottom, that is equal to top. And perhaps a more interesting one, the least upper bound of 1 and 2, so two incomparable constants here. And remember, the meaning of the least upper bound is the smallest element in the ordering that's bigger than everything over which we're taking the least upper bound. So we just have two things here in our least upper bound. But the least upper bound of 1 and 2, the smallest thing that's bigger than both of them, or greater than or equal, I should say, to both of them, is top. Okay? And so the least upper bound then, if you think about it, if you draw our picture again, so we had bottom and we had top, and if you pick out some points here, let's say we want to take the least upper bound of bottom and 2, you're just picking the smallest thing that's bigger than both. Well, that's going to be 2 itself. Similarly, 2 and top, you will get top. And then if you have anything that's incomparable, then you have to pick something that's bigger than both of them. And in this case, that will always end up being top for this very simple ordering. All right, then given this idea of a least upper bound, it turns out that rules 1 through 4, all they're doing is computing the least upper bound. So the in of a statement is just equal to the least upper bound of the out of all the predecessors. All right, that's all that rules 1 through 4 was saying. And if you remember what we had there, we have a bunch of predecessors, and then there's some kind of a statement S. And all we're doing is whatever the information is on these predecessors, we're just taking the least upper bound over it. All right, and that is the information on entry to S. The ordering on abstract values also helps to clarify another important aspect of our analysis algorithm, which is why it terminates. So remember that the algorithm's termination condition is to repeatedly apply the rules until nothing changes, until there's no more inconsistencies in the control flow graph and there's no information left to update. Well, just because we say we're going to repeat until nothing changes, that doesn't guarantee that eventually nothing changes. It could be that that goes on forever, that we always introduce new inconsistencies with every update, and we never actually get to the point where all the information is consistent. So the ordering actually shows why that can't happen, and the algorithm is guaranteed to terminate. So remember that at every program point except the entry point, the values start as bottom. So they start at the lowest place in the ordering. And then if you look carefully at the rules, it's easy to see that the rules can only make the values increase at a program point. So bottom can be promoted, can be changed at a given program point up to some constant, and another update could raise that constant to top. But of course, once we get to top, there's no greater element, and if the rules can only make the elements increase, then eventually we have to run out of elements that can be increased. Okay, so what that says is that each piece of information we're computing, for every statement, for every variable, and for either in or out, it can change at most twice. Okay, so it can go from bottom to a constant and from constant to a top, but after that, it will never be updated again. And what this means is that the constant propagation algorithm that we've described is actually linear in program size. So the number of steps is going to be bounded by the number of C values that we're trying to compute times 2, because each one of those could change 2 times. And since there's one value for the entry and exit over the in and out of every statement, the total number of steps that the algorithm could possibly take is the number of program statements times 4.